Okay, ID number 111, are you there? Hundred and 12,
Yes, sir.
114, 115, 116,
Present, sir.
117.
Present, sir.
Thank you. Just one announcement, I think I forgot to mention it. So all these groups that I've made for scribes are based on all of you who have registered on Moodle. Okay, so if you are a student in section A and if you're still not registered on Moodle, you probably have not been included in any group. And in that case, I will not consider so for example, which is why I've explicitly mentioned excluding ID 113. I don't know if this ID exists. It certainly does not exist on Moodle. So therefore, in case you are not put in a particular scribe group, that means your scribe submission is not considered as of now. Okay.
Hello, sir.
Yes.
I have one doubt in last lecture.
Okay, go ahead.
How every row transformation matrix is a lower triangular. I mean,
Okay. Not every row transformation so just because of the sequence in which we are doing row transformation, the row transformation matrix will be a lower triangular matrix. So if you remember the sequence, it was like use row 1 to eliminate entries in row 2, row 3 to row n, right?
for reducing into echelon form, we only need lower triangular.
Yes.
But in general, it can be lower triangular or upper triangular.
Yes, or neither.
Either. So this elementary matrices mean those which can represent every row transformation.
Yes.
Okay, thank you.
Here, just because of the choice of the sequence in which we are planning to get the row reduced echelon form or the echelon form matrix from a given matrix A, that is the only reason why all elementary row transformation matrices are lower triangular. Okay. Okay, I think we can begin. Right, so we just saw the LU decomposition for any matrix A. It may or may not require a permutation matrix, but otherwise any matrix A can be written into a product of two matrices. One would be a lower triangular matrix, the other would be an upper triangular matrix. Okay, in order to obtain this, we will strictly follow the sequence as I just mentioned. We will first focus on the first column of the matrix A, and for now let's assume we do not require any permutation. So we use the first entry of the first column in order to obtain zeros below it, which means, I just said, we use row 1 in order to obtain zeros in column 1 of use row 1 in order to obtain zeros in column 1 below entry 1. Once that is done, we use row 2 to obtain zeros in the second column below the entry 2, below row 2, okay, and so on and so forth. So n minus 1 will be used to obtain zeros in column n minus 1 below entry n minus 1. Is that clear to everyone? Okay. And if we assume that the matrix A is a square matrix of size n, then as we did in the previous class, the total number of computations is roughly like 2 by 3 n cube. Okay, and I think the question that we left is, are these computations going to give us only the matrix U or both the matrices L and U? Okay, if these number of computations give you only the matrix U, then how many more computations would we need in order to compute the matrix L? And that is the question. So has anybody thought about this?
Yes, sir.
Yes, go ahead.
Sir, in order to form the matrices from the n into n minus 1 by 2 row transformation, we will not require any computation because we have already found all scalars. But and then we can convert this n into n minus 1 by 2 LIs to get, means we can reduce it into n minus 1 matrix multiplication, but then we have to multiply.
So you think we need additional computations to get L?
Yes, sir.
Okay. Anybody else thought about this?
Sir, I think we haven't counted for it, but if we count, then it will also come n cube.
So that means it will be plus n cube if I am talking about obtaining L and U both.
Means I have not counted coefficient, but order of n cube. L will be also.
Acha. Okay. So, but basic conclusion is you will need something more, which is roughly of the order n cube. So the total will still be of the order of n cube.
Yes.
Okay. Anybody else?
Those
Can you please
scalars,
repeat
the scalars which we like, while
Yes, go
performing
ahead.
this, or when we find those scalars while performing these operations, then from those scalars we can build the L matrix.
So no additional computations.
Yes.
Okay.
And sir, can we do that if we have A and U, then find L? Okay, so no, it will be also like again another.
Still, exactly. You are still going to solve n systems of
Yes,
linear
yes.
equations, right? So yeah, the basic point is, do we need more computations in order to get L, right? These computations, the way we listed them out, we sort of said we need these to get U, but do we need more? Because I'm trying to compute the number of computations in order to obtain the decomposition, right? So decomposition involves two matrices, both L and U. So just obtaining U is not enough. We are trying to find both L as well as U. Okay, so that is the question, and 2 or 3 of you have tried to think about this, which is good, but I hope more of you can get involved in this. So let us try to figure this out. Okay, right? So if we continue along the same flow that we did in the last class. So we all agree that we might have, or we have to spend these many computations in order to get U, right? How do we compute L now? That is the question. So let's observe this. Okay, so I hope these notations are clear. EI, right, is an elementary row transformation, right? What does EI represent, right? EI represents the elementary row transformations required to obtain zeros below the leading entry in column I. Okay, so there is a slight deviation from what we followed in the previous class. In the previous class, it was like if this is your matrix A, let's say 3, 2, 1, 1, 2, 3, 4, 5, 4, something like this. Then we used R2 to be R2 minus R1, something like this, or also write it in the form of R2 minus R1 by 3, right? So as to get a 0 here below 3, right? And we don't care about anything else. And then the next step is use a row transformation between R3 and R1, right? So as to obtain the 0 here. Rest we don't care. Right now, if we look at this, we can combine both these row transformations into one. As one of you, I think, already pointed out when you were looking at that 4 by 5 matrix example. Right? We could combine both of these row transformations into one matrix. Is that okay for everyone? So what would the matrix look like? I would then, using this notation, I would denote it by E1 because I'm using these transformations to obtain zeros in column 1 below the leading entry in that column. So how would that matrix look like? Am I doing anything to row 1? No. So 1, 0, 0. How about row 2? What would be the second row?
Minus 1 by 3, 1, 0.
Minus 1 by 3, 1, 0. Row 3?
Minus 1 by 3 only.
No, why minus?
No. Minus A. Minus A.
Minus A, then
0, 1.
0, 1.
0, 1.
Right. Okay, so try to observe that in each EI, right? So in this example, in E1, you would have non-zero or non-identity entries only in the first column. Okay, why? Because we are interested in bringing zeros in the first column. Okay, similarly, EI would have entries which are different from an identity matrix only in column I. Yes?
Yes, sir.
Okay. And EI is going to be enough in order to bring zeros in whatever number of zeros we need in column I. Right? And since in order to transform A into U, if A has n columns, and if each EI represents all row transformations required to bring as many zeros in column 1 as in column I as required, we'll need n such elementary row transformation matrices in order to transform A into U at max, of course.
Sir, will you repeat?
Sir, I think we don't need En.
Oh, sorry, yes, that's right.
Yes, sir.
That's right. En minus 1, yes. Thank you. Okay, I'll repeat this. See, each EI, as you can see in this example, is going to be enough to bring the required number of zeros in that particular column I. Yes, Pujan, is that
Yes,
fine?
sir.
Okay. So then how many such E matrices will be required at max? If
and minus.
exactly, if the matrix A is of size n by n, the matrix U will also be of size n by n and it will be upper triangular. So in order to transform A into U, if EI is going to do the transformation, do the required transformation for column I, since A has n columns, we'll need at most n minus 1 such transformation matrices.
But sir, if one means if EI changes ith column, so
Mhm.
in
So
EI
just
plus
a minute,
1,
it doesn't only change ith column, it sort of brings zeros there. That is important.
okay,
Okay, then go ahead. So let's say this is E1, right? This much. Then you'll have E2. So what is your
so
question?
so for E2 we have to make zeros in second column below the leading entry.
Yes, so the leading entry is this in square. Or maybe I should use a different color. Right? This is my leading entry.
Yes.
Right? So I will need one row transformation to bring zeros over here.
Hmm.
Okay?
Okay. And in last column there will be no. That means we will not require to make any zero.
Yes. So that is why n minus 1 such row transformation matrices at max will be required.
Yes. Sir, okay. I got it.
Okay. It may so happen that you may require fewer than n minus 1, but maximum is n minus 1. Right? It may so happen that while you are bringing zeros here, this entry also goes to 0. Or when you are getting zeros here, this entry also goes to 0. In that case, you won't require E2 at all. Okay, but maximum is n minus 1.
Yes. Sir.
Okay. So now, if so just assume n is n minus 1 because in all the next few slides I am using En, which is of course a mistake from my side. So then L of course has to be the product of inverses in this order. Right? I hope that is understood. And then I can also look at it this way, right? If I multiply or if I perform the same elementary row transformations that I performed on A in order to get U, if I perform the same elementary row transformations in the same order on the matrix L, then I should get I, right? Okay, because this is the inverse of this.
Yes.
Okay. So now, what does the matrix E1 into L look like? So assume L is n by n, E1 of course is also n by n, and E1 does something specific, right? It brings as many zeros required in column 1 of the matrix A. What does the same E1 do to L?
It will also bring zeros to first column of
First column of
L below leading entry.
L, right? So then the first column of the matrix L should look like this. And these are all zeros, and this everything else we don't care. How many of you agree with this? this is sort of the most tricky part here. Somebody raised a hand, I believe. Yes. Anybody who does not agree with this? That by applying the even elementary row transformations on the matrix L, whatever that matrix is, we do not know it yet, but let's say we knew what is L, and if I were to apply the elementary row transformations E1 on L, that would also make or turn the first column into 1 followed by all zeros. Anybody who disagrees with this? No. Okay, great. Similarly, of course, how does E2 even L look like? If you know what is even L, then you also should be able to give me this. Be 1 followed by all zeros, 0, 1 followed by all zeros. This will all be 0, and all of this we don't care. Right?
Yes, sir.
Yes, sir.
Yes, sir.
So now can you tell me how many additional computations do we need in order to get the matrix L?
n-1 whole square.
-1 whole square additional computations. Anybody else? What does this tell us about L? What would be there in the first column of the matrix L? If you agree with this and this,
Sir, will it be summation k from 1 to n-1?
in the number of computations?
Yes, for this entire one. Meaning there will be n-1 multiplications
No, just a minute. I'm not asking you that how many computations do you need in order to compute even into L. My question is, if you agree that even into the matrix L is this kind of a matrix, right? And if E2 into E1 into L is this kind of a matrix, right? My question, first of all, right, is what do you think is the first column of the matrix L? Okay, I mean, we know all the rest is this over here. So we know it's diagonal and upper triangular part. Forget this part. Can you tell me what would be the first column of the matrix L? If even into L looks like this, what would be the first column of the matrix L?
Same as a
Same as L, but L
A,
is something we don't know.
A.
Same as A. Why would it be same as A?
Because we apply even on A. No.
the scalars for
What?
the scalars while transforming first column of a to 0.
Would it be the same scalars?
Then I think negative.
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 Right? So if even looks like this, 1 even to En, 1, 1, and everything else, of course, is 0 because of the way even is designed, right? It only does the work for the first column. Okay, so if this is my E1, my L, the first column of L has to be this.
Sir, won't it be E1 to En minus 1?
Oh, sorry, yes, again. Yes, En minus 1. En minus 1 here as well. Okay, just write this. En minus 1 and minus. Think about it. Can the first column be anything apart from this? See, the first column of E1 into L, what is that equal to? This has to be equal to E1 into the first column of L. Right, let's call it L1. This should be equal to 1 followed by all zeros, right?
Yes.
So now I think it is easy to solve, right? And of course, remember, the first entry of L1 has to be 1 and the rest are unknown. These are unknowns. So now it's just like n equations or n minus 1 equations in n minus 1 independent variables, right? Because if you look at the matrix E1, apart from the first column, everything else has no information, right? I mean, is this understood, or do you want me to sort of give you more details of this? Anyone who wants me to derive this?
Yes, sir.
Okay. So let's say E1 is this matrix, right? 1, E1 to En minus 1, 0, 1, all zeros, and so on and so forth. This is all zeros, this is all zeros, right? This much I hope you agree.
Yes, sir.
Okay. And E1L is the first column of E1L is this 1 followed by all zeros. Okay. The first column of L is, let's say, 1, and the variables are x1 to xn minus 1. Okay. Here is 0, everything over here I don't care. Okay, so if I rewrite this equation, what will I get? E1 into L's first column, what would that be?
1 0 0 0 0 0.
No. The left hand side, if I multiply this E1 into L and look at it, it's 1 times the first column, right? So it's this plus x1 times the second column. What is x1 times the second column? 0, x1, all zeros. So on and so forth, plus xn minus 1 times the last column. 0, all zeros, xn minus 1. This we want should be equal to 1 followed by all zeros. Right? Now can you solve it? I think it's easy, right? 1 plus all zeros is equal to 1, no problems. E1, okay, so x1 would be minus E1 and so on and so forth. Xn minus 1 will be minus E10. So that's the first column of the matrix A. So how many computations have we performed in order to know the first column of the matrix L?
0.
0, right? 0 additional computations. Okay, once we know what is the matrix E1, from that matrix E1 we can easily find the first column of the matrix L without performing any additional computations. And of course, if this applies to the first column, it applies equally well to the remaining columns as well.
Should we ignore that cost of finding negation?
So that's not any, I mean, we are not finding it, right? The only thing we do is to flip the bit sign.
Yes.
Right? So there we don't perform any computations. It's just a memory manipulation, right? It's not really like adding. You're not going to use the ALU in order to do this. All right?
Yes, sir.
Okay. So is it clear? LU decomposition requires, what
Yes.
was it? Some horrible number, 2 by 3 n cube. I don't remember the constants here. Okay, in that. Right, n square by 2 and n by 6 number of computations. Right, and how about inverse? How many computations? And again, using the same row reduction, the only thing is now the row reduction is performed also above the diagonal, right? So how many total computations? I think we are running out of time. So can I leave this as an exercise? I think roughly, I believe, is 2n cube or n cube, something like that. Okay, so you don't stop only at L and U. You sort of proceed in order to further row reduce the matrix U to obtain the matrix I. Is that fine? Yes or no will help me.
Is it just a double of what we
I think
completed last
it's
time?
at least double, but I think you need more than double, if I'm not mistaken. Okay. I think it is 3 times, if I'm not mistaken. So work that out, otherwise we can discuss this post the run. But the process, I hope, is clear to everyone, right? You just have to continue doing the same, or you don't have to stop at an upper triangular, but you continue doing it so as to obtain the identity matrix, right? Okay, so let us for now agree. Of course, the important conclusion, that irrespective of which of the two is the answer or something else, is that this is again a Pico of n cube algorithm. Right? So in some sense, I mean, you look at it this way, it would be a little bit of a surprise. If I have to multiply 2 matrices, or in fact a matrix and a vector, how many computations? Let's say matrix with matrix of size n cross n. How many computations?
N cube.
N cube.
Order of n.
Right? And this is sort of this of computing A inverse has the same complexity. Right. So LU decomposition requires n cube, A inverse requires n cube. How about solving linear system of equations? How many computations does that require? So if I try to solve this linear system of equations using LU decomposition followed by back substitution, LU decomposition, we have seen it is big O of n cube, and to be more precise, it is something like this, right? How about back substitution?
It will be order of n.
Is order of n?
Yes, sir,
Why?
because for each row we are finding xn by minus of bn by the minus of bn by the scalar multiple over there.
Right. So in order to solve this last row, how many computations do you require?
So one computation.
One.
One. How about the second last row?
There are also one
One.
computation.
How
Because
one?
we have already computed.
Value substitute.
But you'll have to substitute it here, right? So xn is, let's say, some bn by an, and then you have some cn minus 1, xn minus 1 plus cn xn equals to bn minus 1 as the second last reduced equation, right? So you'll still
Yes.
have to do this, isn't it? Minus bn by an. This you already computed, but into cn and then divide by cn minus 1. Okay, so it won't be only one computation, right?
So it will be 4 computations.
4 computations.
3 computations.
3.
So 2 multiplications.
Oh yes, sir. Bn by n is already being computed. Yes. Then
Yes,
3
this is already there. And 1 addition or subtraction. Okay, how about this?
5 computations.
So 3 plus 2, I believe, right?
Yes.
So now can you tell me roughly, is it order of n? Is it order of n?
Order of n squared.
N squared. Okay, so this is order of n squared. So should we use LU and then do this Ly equals B and then Ux equals Y, or should we just compute A inverse B as X? Which of these two methods will you prefer and why?
First method will take less computation.
Why?
It is order of n
The
square
first
for
step is also
One at a time. Maybe Gangaraju, could you complete your answer?
Ly equal to b needs order of n square for finding y,
Okay.
and ux equal to y also need order of n square.
Okay. How about this?
Inverse needs order of n cube. And matrix multiplication is order of n cube.
This is n cube. Why?
And multiplying two matrices.
No, B is not a matrix. I mean, it's a column matrix.
Sir, A inverse, calculating A inverse will take.
Order of n cube, right?
Yes.
It will take order of n square, A inverse b.
A inverse B takes order of n square again. But when you are saying that we need order of n square here, you're forgetting that you also need LU, right? And nobody is going to give you LU directly. You will be given A matrix, right?
Yes, sir, yes.
Sir, we don't need a space for because if we do A inverse, then A will change. So we can't get our A back. So we need space for.
No. Just a minute. Why? I mean, A is a matrix which is given to you, right?
Yes. So if we do LU decomposition, then A will remain same. But if we find A inverse, so we need another space for to copy A in another and then find A inverse, or
Yeah,
we
but
have to do it in A also. So we will forget our A in.
no. But the same holds here. In fact, here you need more space to store the matrix L and matrix U, isn't it?
Yes, sir.
Sir, I will choose LU decomposition because A inverse does not exist. Means A inverse does not exist all times.
No, okay. So leaving apart that question, whether A inverse exists or not, which is of course a very valid point that you have made. But for now, let's assume A inverse exists.
Sir, storing L and U will take the same space as storing A.
Sir,
Right.
A inverse method would be more better, I think, because in LU decomposition we will have to perform two operations of order n cube and two
Where
operations
are
of
two
order n.
operations of order n cube?
So in finding L and in finding U both.
No. Both of them put together. We just described that, right? Both to compute L and U together, you need big O of n cube, or to be more precise, something like 2 by 3 n cube. Right? We just made this huge presentation where we said
Yeah,
that.
sorry.
No, that's okay. So, which method will you prefer?
Sir, in LU decomposition, I think we can also find the case when the solutions are not unique. Means,
Agreed. Yes, I completely agree with you. But in case, my question is still, in case where A is invertible, which will you prefer? Okay, so big O of n cube, if I just say big O of n cube, then both of them are going to cost the same, right? Here also you have big O of n cube and big O of n square. Here also you have big O of n cube and big O of n square. So the devil lies in the detail. Big O of n cube is I can in principle distinguish between algorithms in this class, right? So what I'm trying to say is this constant matters. Okay, so here it is 2 by 3 n cube, and as I said in computing A inverse, I don't remember precisely, it's either n cube or 2 n cube, one of the two. Yeah, something like that. So it is sort of twice or thrice more computationally expensive to compute A inverse. Okay, and therefore, of course, I will prefer the LU decomposition. All right. You guys seem to be disappointed. I don't know. Okay, there is no need of computing L inverse here. Sorry, A inverse.
Yes, sir.
So these were sort of the portion of linear algebra which sort of is an extension of what you already know in some sense. Linear systems of equations, both the theory part as well as the practical portion. Let's now try to get back to the original spirit of the course, which was to examine structures. Okay, so we will now move on to looking at a particular algebraic structure which is called vector spaces. Okay, and I'm going to try and convey this as if it is an extension of what we were doing till now. Okay, so all of you are familiar with linear combinations, right? We have used linear combinations while studying what happens when we multiply a matrix to a column and so on and so forth, right? So till now we have seen, let's say, linear combination of elements in R2, right? A two-dimensional XY plane. Yes, so by linear combination, we mean something like this. We take two arbitrary real numbers, we take two arbitrary elements in R2, and then this is sort of the notation for linear combination with AX and BY, right? And this is how it looks like. Of course, you can rewrite it as AX1 plus BY1 and AX2 plus BY2. Okay? Right, so I hope this is nothing new here. There's nothing new here, right? Now, why just R2? Right? What is so special about this set R2? We can also do this for R3, right?
Yes, sir.
Okay. Why R3, right? I mean, you can do this for any Rn. And what I want you to look and observe here is the common, I mean, there seems, although the sets in themselves, R2, R3, Rn, or n different from 2 and 3, they are very different. But as far as linear combination of elements are concerned, there is a commonality here, right? Try to recollect our first lecture. We are sort of looking at different things, but we are trying to observe that there is a common essence. Right? So we have had examples of hundreds of chairs, which in principle are different, but there is a commonality to the structure of a chair, right? So here also, as far as these two operations are performed, one is multiplication by a real number to an element of the set you are looking at, and the other is adding two elements from the set. They are sort of behaving very similar, right? And so therefore, why should I restrict my attention to only R2, R3, Rn? Let us do something more. So let's X and Y be elements of this set. I don't know if you're familiar with this set. This is the set of all. I'm sure you've seen this in a different course in this semester itself. I hope so. Doubly infinite real value sequences. Have you seen this set before? I mean, not before, in the same semester somewhere. So an element X
Yes, sir.
in this RZ will look like something like this. X minus 2, X minus 1, X0, X1, X2, so on and so on. Where each Xi is a real number. Where have you seen this?
Direct product.
No. Signals and systems, right? What is this sequence trying to model?
Sir, a signal. In
What sort
discrete
of a
time.
signal?
Undiscrete time.
Discrete time signal.
Discrete time sequence, right?
Sir,
And an
here,
infinite sequence. Yes.
sir, here all xi belongs to real number or alpha raised to I means.
No, real number. Each xi is a real number, and since I have an infinite sequence of real numbers, that is why I'm using this notation r to the power z. Okay? This is not necessarily a very standard notation, but I couldn't think of a better notation. So don't get confused because of the notation.
Sir, what he do here in RST Z, this Z represents the set of all integers?
Yes, yes, yes. That is the same Z. Yes.
Okay.
Okay, because integers are like minus infinity to infinity, so that is why I chose that. The index of each is an integer.
Okay, sir.
Okay, so once again, this is not a standard notation. Okay, r to the power z. So in case you don't come across this notation in any book, don't accuse me. Right?
Sir, can you not represent it using r raised to infinity?
The only thing is then, then this is r infinity. Yeah, but then something like this also. How do I differentiate between
Yes,
these?
then it will be like a ray.
Yeah, or a sequence. I mean, in terms of signals and systems, this is a signal that starts at
Time
a certain
0.
point, right? So yeah, once again, I mean, repeat this. There's nothing special or standard about this notation. Don't just get confused because of this notation. Okay. Right. So if I have this sort of a sequence, I can also go ahead and define a linear combination in this way. Right. I can take two scalars a and b, take two such doubly infinite sequences of real numbers x and y, and then do the same thing that I've been doing here, here, and here. And what I've been doing is multiplying this real number to each entry in this vector, and then all I'm doing is doing an element-wise addition. Right? Corresponding elements get added to corresponding elements. So the same thing I can do with sequences because there is a unique index available with me. So ax0 I can add with by0, ax minus 1 I can add with by minus 1, ax1 can be added with by1, and so on and so forth, to again obtain a doubly infinite sequence of real numbers. Right? You have probably already done this, isn't it, in your signals and systems course? Have you?
Yes, sir. Addition of two
Where?
signals. Addition of two.
Exactly. Addition of two signals, right? The point I want to convey here is, unless you have vector space, which is something that you don't study in signals and systems, you cannot add two signals the way you are talking about it. Okay, so that I will make it more clear in the next few slides. Why should we stop at sequences? Why can't we work with analog signals or continuous time domain signals as you are studying in your signals and systems course? So let us consider the set. Again, this is not a very good notation, I agree, but maybe in a hurry, I just couldn't think of a better notation. Set of all real valued functions defined on the set of real numbers. Okay, if I take two such functions and take two arbitrary real numbers a and b, I can go ahead and define a linear combination in this way, right? So a into f plus b into g. Okay, I have to define what this means, right? So what I'm trying to say here is I'm trying to show that a into f plus b into g can be defined so that it belongs to this same set of real valued functions defined on R. This has to be in this set. So how do I show that? Since this has to be a function, I can define a function by conveying what is the value that this function takes for every real number. Okay, so a into f plus b into g is a function whose value at any given x is this. So the value of this new function at x is nothing but a into the value of the function f at x, which of course has to be a real number by definition. A is also a real number. plus b, which is also a real number, times gx, which is also a real number. Okay, and therefore a into fx plus b into gx will also be a real number. Since x is arbitrarily chosen, so af plus bg, this new function, also belongs to this set. Okay, and again, I'm more or less certain you have done this already in signals and systems, right? Adding two continuous time domain signals. Yes? Is this clear?
Yes, sir.
So again, it seems to be a common structure here, right? I mean, the elements, the sets are very different. But as far as we look at linear combination, there is hardly any difference between all of this. So the commonality or the essence of all of this is the structure that we call vector space. Okay, so let me define what is a vector space. A vector space, right, is a set, first of all, V, equipped with another set. Okay, so if we look at the above examples here, you can see that we had two sets in each example. If I take up this example, one set is Rn, and the other set is the set of real numbers. Right? In this example, one set is containing elements where each element itself is a doubly infinite sequence, and the other set is the set of real numbers. This example, taking the set of all real valued functions defined on R. So each element is a particular function. Apart from this set, I have also considered the set of real numbers. Okay, so in all of these examples, this second set, which happens to be the same set R, right, that plays the important role of giving you these scalars, right? So therefore, the vector space structure sort of requires two sets. Okay, it's a set V. The other set is what is called a field. Okay, a field is yet another algebraic structure. The definition of this will follow in the next couple of slides. Okay, so field itself is a set which I'm in general going to denote by F. So if this F is confusing you, and if you have followed the previous example, for now you can think F as the set of real numbers. Okay, and a field is not only this set. Apart from this set, you also have two binary operations defined on them. One is what we usually call addition, and the other is what we usually call multiplication. Okay, so a vector space is a set V with a field F and its operations. Apart from these two sets, the set V should also be equipped with two binary operations. Okay, so if you look at this plus, I've deliberately used different notations here. This is plus defined on the field F. Okay, whereas this plus is defined on P. Okay, so you have two binary operations. One is vector addition. The other is what we call scalar multiplication. Again, still a multiplication, but I am using a different notation so as to differentiate between this multiplication and the multiplication between elements of the field. Okay, so there are in principle four things. You have the set V, you have a field, and on V you have a plus and a scalar multiplication defined. Definition itself is not enough. All these four have to satisfy axioms. Okay, just like a set and a binary operation, if they satisfy certain axioms, they form a group. Similarly, a set, a field with two binary operations that satisfy the axioms that are going to follow, then that set is what is going to be called a vector space. Okay, so let me specify the axioms. First is easy. A set V with this particular addition operation, that should form an abelian group. Okay, so just to give you an example from the previous case, if I look at R2, right, and the addition which is defined in this way, x1, x2 plus y1, y2. Now, if you look at this, this is a tuple, this is a tuple. There is in principle no natural way of adding two tuples. We know how to add two real numbers, but we do not know unless we define, right, how to add two tuples. So one natural way to define this would be x1 plus y1 and x2 plus y2. Okay, and you can clearly see that this R2 with this particular addition operation will form not just a group but also an abelian group. Okay, so in the first axiom, the field has no role to play. Therefore, I hope this axiom is easy to understand. Yes? Is this clear?
Yes,
Okay.
Yes, sir.
Yes, sir.
Throughout this course, once again, I will use this notation theta for the additive identity. The problem is you will see that there are two operations, so that you may have two different identities, right? So therefore, I am going to stick to this notation. Theta will denote the additive identity. Okay, so in previous module on groups, we usually denoted the group identity by the letter E. Instead of that, I am going to use theta here. Okay, next axiom is with the scalar multiplication. Okay, so in an abelian group, remember there is a closure property. So similarly, right, the set V must be closed with respect to the scalar multiplication. Now, scalar multiplication is something that is not defined on two elements of V. Okay, the scalar multiplication is defined as a binary operation whose first argument comes from the field. The second argument comes from the set V, and the scalar multiplication, there is a typo in the notation here, it should be this. Okay, the scalar multiplication takes elements from F cross V, the Cartesian product of F and V, and gives you back, it should give you back an element in the set V. Okay, so again, if you look at all these examples here, right, this is scalar multiplication, this is scalar multiplication, this is scalar multiplication. Notice this is very different from your usual multiplication. Okay, the first element is a real number, the second element is a tuple of real numbers. Okay, so they come from very different sets. Similarly, here in the last example, right, A into F, here A comes from R, F is a function, right? So it comes from this set. So as far as elements are concerned, these are very different entities. Okay, so that is sort of a differentiating factor between the usual multiplication and a scalar multiplication. Okay. Right. So the set V has to be closed with respect to the scalar multiplication. Any doubts here?
Sir, here will the multiplication be the multiplication of the field or multiplication in vector space?
No, so this multiplication, when I say scalar multiplication, it is this multiplication. Okay, and this are going to be very different. So think of F as set of real numbers. Think of V as set of n tuples of real numbers. Okay, so I need to define a way to combine R with Rn to give Rn, an element in Rn.
Yes, sir. Yes, sir. Now I got it.
Okay, so one way to do it, and which is a natural way again, is this. A is a real number, x1 to xn is one element of Rn. The multiplication between these two, I can define it in this way. Ax1 to axn, where ax1, right? This is multiplication between just two real numbers, right? And that is defined from the field. Okay, so if it is about notations, then
Sir, this scalar multiplication need to satisfy only one condition, that is closure.
No. There are several more. Just listing them one by one. Okay, so you can see if I define it this way, right? My set Rn will be closed. Why? Because x1 to xn are real numbers. A is a real number. A into a real number will also be a real number. A into xn will also be a real number. So therefore, this vector will be an element in Rn. And therefore, this way of defining scalar multiplication, right, is going to satisfy the closure property. All right.
And
So yes, go ahead.
And so the multiplication of A with xi, will it be the multiplication in field?
Yes.
Okay. Okay, sir.
So this is one way of defining it, right? So this is just one real number. This is one real number. So multiplication between two real numbers comes from the field.
Sir,
Yes,
if
sir.
we define this scalar multiplication in some different way, like A times this scalar vector, or A times this vector is A plus x1, A plus x2,
Yes.
like that.
Yes, you can define it. But
Sir, here this scalar multiplication and addition, this both are means clashing. Both
no,
have
why are they
same
clashing?
exact.
See, vector addition is defined between two elements of my set V. So this is your vector addition. Right? Scalar multiplication is about combining a field element with an element of my set V.
Okay, sir, got it.
Okay, so I maybe write it clearly. Plus is defined from V cross V to V. Scalar multiplication is defined from F cross V to V. And these are very fundamentally, they are very different operations. But just like groups, they are not hardwired, right? You can define group operations as you wish as far as they satisfy the axioms. The same holds true here. Okay, it's just that in all the examples, so vector space is something, let me tell you, you have been using it without your knowledge even in your school days. Right? And there is a natural way that you have been using all these scalar multiplications and vector additions, right? I mean, the operations that I defined in the previous slide, they are not new. You have been using this one way or the other, at least for these two examples. Okay, but in principle, you are free to define scalar multiplications and vector addition the way you want, as far as properties that I'm going to list are going to be satisfied. Clear?
Yes, sir.
Yes, sir.
So let's look at the other properties, especially with respect to scalar multiplication. Another property is there has to be an identity element in my field for the scalar multiplication. Okay, so don't get confused here. When I write 1, it doesn't necessarily mean the number 1. Okay, means there must be some element in my field F that I am denoting as 1, such that if I perform a scalar multiplication with that particular element of the field with any vector or with any element V on from my set capital V, I will get back the same element V from my set capital V. Okay. The next slide, I will give you examples of fields which are not numbers also. Okay. So I think that then it will be clear. What I mean by one is what I mean by one is, I mean, here I'm defining what is one here. Okay, take it that way. Okay, let's look at the next property, distributivity. Okay, so there are two distributive properties here. For any field element A and for any elements U and V from my set capital V, scalar multiplication of A with the vector addition of U and V must be the same as scalar multiplication of A with U plus scalar multiplication of A with V. And similarly, given two scalars A and B from the field F and any vector Q from my set V, the field addition between A and B must give me a field element whose scalar multiplication with U has to be the same as scalar multiplication of A with U, vector addition with the scalar multiplication of B with U. All right. Remember, once again, I'm using a different notation here just so that you don't get confused. This is field adding elements of fields. This is adding elements of my set V. Okay, so whenever you get confused, in the prototypical example must be, I mean, you can think of it as this way. V is Rn and the field is R. Okay, then I hope you see that as sets and their elements, they are very different. Okay, so adding two real numbers is not the same as adding n tuples of real numbers, although adding real numbers is naturally used in order to define adding n real numbers or tuples of n tuples of real. In this one more property, compatibility of the field and scalar multiplication. That means is if I take any two arbitrary elements from the field F and take an arbitrary vector U, if I first do a field multiplication of A and B in order to get an element, a new element of the field, and then perform a scalar multiplication with U, I should have the same thing as first doing a scalar multiplication of B with U, with which I can perform yet another scalar multiplication with the element A from the field. Okay, so there are sort of, in principle, 9 properties. I mean, if you remember, abelian group itself needs 5 properties, right, or 5 axioms plus these 4. So in principle, there are 9 properties that the set V, the field F, and these two operations have to satisfy. Now let's talk about the field, right? So a field is a set F with 2 binary operations. Should be capital F. Addition and multiplication. Yes?
Sir, can you show the previous slide for one second? Okay, sir, done.
So field, let me quickly define this. It is a set with these 2 operations that satisfy 3 very simple properties. First, as expected, the set F with the addition operation is an abelian group. Okay, and once again, I'm going to denote the additive identity in the field by the number 0, or that is the notation. Don't take it as a number. Okay. So this is different from the additive identity of my set V in the previous slide, which is why I need a separate notation. I hope you can appreciate this. What more? If I remove this additive identity from my field F, then the remaining set with the multiplication operation should also be an abelian group. And for this abelian group, the identity will be denoted by 1. All right. Again, if you're finding this difficult, think about set of real numbers. Okay, so real numbers with your real number addition forms an abelian group. And if I leave out 0 from the set of real numbers, then real numbers minus the set 0 with real number multiplication, that also we know that it forms an abelian group. Okay, and the multiplicative identity element will be denoted by this notation 1. So if you look at these two properties, it seems as if the addition and multiplication have nothing in common, but of course, distributivity has to be satisfied. Okay, so these are the usual distributivity properties that all of us are familiar with. Let me give you examples of fields so as to make it clear. Set Z2 that we had seen, I think, in groups. Okay, so 0 and 1 with addition modulo 2 and the usual integer multiplication. That you can see that it forms a field. Right? You already know Z2 plus 2, right? Addition modulo 2, we have proved that this is an abelian group, right? And if I remove 0 from Z2, that means I have only this element 1. And with respect to multiplication, this also forms an abelian group. Okay, so that is one example of a field. Set of real numbers, just sort of discussed it briefly, that also forms a field with your usual real number addition and real number multiplication. Other examples, set of complex numbers. As far as signals and systems are concerned, this is a very, very, very important field. Okay, you use it in your signals and systems frequently. Okay, set of complex numbers with your usual complex number addition and your usual complex number multiplication, that also forms a field. Set of rational numbers, again with rational number addition and rational number multiplication, that also forms a field. Now, if you look at all these 4 examples, these are all numbers, right? They are basically subsets of real numbers. So let me give you an example which is not a number. That is the set of all rational polynomials. Okay, so what do I mean by rational polynomials? I'm basically going to take a ratio of 2 polynomials. The only condition is that the denominator polynomial should not be the 0 polynomial. And the 2 polynomials involved are polynomials in one variable with real coefficients. Okay, so the set of all such rational polynomials with your usual addition between functions and multiplication between functions. Okay, or multiplication between such polynomials, that also forms a field. Okay, you can later on quickly just verify the properties. Okay, so this is, for example of a field which is not just numbers. So to bring this back to this, whenever I say 0 from the field and 1 from the field, right, don't think of it arbitrarily as the number 0 and the number 1. Okay, they denote the additive identity and multiplicative identity respectively of the field. So I think that's it. So if the three tuple in this is the set with these two binary operations and the field, if they satisfy all vector space axioms, we say that this tuple forms a vector space over the field F. And once you have a vector space, any element of the vector space will be referred to as a vector. Okay, so this is slightly different from what you are familiar with. Whenever we say a vector, you always think of some finite R2 or R3 and an arrow that sits at the origin with the tip lying somewhere. Right? In contrast to that, I mean, it's not really contrast, but this is slightly different. Right? We have seen vector spaces that will contain functions. So every function will also be a vector. Okay, and once you have a vector space, every element can be referred to as a vector, and any element of the field will be referred to as a scalar. I think we will stop here for today.
Sir,
Yes.
sir, in definition of vector space, we have fields. So, sir, what is significance of the additive identity and multiplicative identity of fields in vector space?
Yeah, so they have to satisfy this property, right? Yeah. This has to be satisfied.
But sir, this need not be additive identity or multiplicative identity
No,
of
this
field.
is, so when I say one, right, just because I had not defined what is a field, I couldn't sort of specify what is this element here. Okay, but this one has to be the multiplicative identity of the field. Right.
So this is in definition that the identity element for scalar multiplication of vector space should be multiplicative identity
Yes.
for field.
Yes.
Okay. And sir, what about additive identity?
What about additive identity? So we will, in the next class, we will prove that. Where should I write it? We will prove this property that for any u from my vector space V, scalar multiplication of the additive identity with this element u must give you the additive identity of the vector space.
Okay, sir. Thank you.
Okay, so this is not an axiom. Okay, please be careful. But we can derive this from the axioms. All right.
And sir, here we are also calling vector space as tuple, right?
Yeah, tuple in the sense that the set and its two operations.
But it also requires field elements.
Yes, yes, yes.
So
Yes.
means it is not complete that we define
So
it vector
like,
space as tuple.
in the sense we will always specify, right? If you look at this, we say that V with this forms a vector space over the field F. So the field has to be specified.
And sir, in field definition, two operations are required to be addition or multiplication.
Oh, so it is just a name that we are giving to it. Okay, the examples of fields that we are familiar with, in those fields, these two operations are usually the addition, the usual addition and the usual multiplication. But you are free to define these two operations in the way you want as far as they satisfy these three properties.
From that means here also the definition is means the operations are flexible to define.
Yes, yes, yes. So please remember, we are looking at abstract structures. In all these at least in these three definitions, whether it is group, whether it is vector space, or whether it is field, the common thing is we didn't specify what is the set we are picking up, right? That set is left arbitrary. So if my set is not specified, right, how can I specify what these operations are?
Yes, sir. Yes, sir.
Okay, so in all these definitions, all operations are flexible. The only condition is that you can define the way you want it as far as they satisfy the axioms. All right.
And sir, in the definition where the field with the scalar multiplication is abelian group, whether the element removed is the additive identity of the group or the number 0.
Once again.
So means in the definition where the field with the multiplication is the abelian group, the element removed, is it the additive identity?
Yes. So
or the number 0.
So the additive identity is what will be denoted by 0. Does not mean that the additive identity has to be the number 0.
Okay, I just means the element removed is the additive identity of the.
Yes.
Field.
Yes.
Okay, sir. I just was having that small confusion.
No issues. It's okay. So again, if you having trouble understanding that whether this is number 0, please remember there are examples of field of this kind. Polynomial, rational functions or polynomial. So each element is not a number, it is a rational polynomial in itself.
Yes, sir. In rational polynomials also the additive identity is number zero.
Is the polynomial 0.
Polynomial 0, yes.
Polynomial yes. 0, not the number 0.
Yes, sir.
Right. So the number 0 is not even an element in this set. So how can it be the additive identity?
Yes, sir. I understood, sir. Thank you, sir. Thank you, sir.
Welcome. Any other questions? Okay, so then we end the meeting.
Sir?
Thank you, guys. Yes, Pandan.
Sir, tensors are also in element of abstract algebra.
Once again?
Tensor.
No, I didn't get your question. Can you repeat it?
Sir, tensor means they are called higher dimensional vectors.
Yes.
So are they elements of abstract algebra?
Tensors are, I mean, if you talk of specific tensors, these are, of course, examples of some algebraic structures.
So which algebraic structures?
So one could think of them as vector spaces also. It depends what is the particular tensor you are talking about.
Sir, in case of the susceptibility of a material, it is a tensor.
Once again?
Susceptibility of any material. Susceptibility of any dielectric material, that is a tensor.
Strain tensors and things like that.
Yes, sir, strain tensor.
That I mean, I don't recall that as of now, at least. But if you're talking of so tensors, no, I don't have an answer to that right now. But I'm sure they are. At least I'm sure that they are examples of most likely vector spaces. Most likely.
Okay, sir. Thank you.
Right. So if there are no more questions, wish you all a happy Diwali and hope to see you guys in the last leg of this course. Yes, Sumin, go ahead.
Sir, for group 3, we have to prove that the positive symmetric definite matrix forms group under matrix multiplication. But we found on net one paper from any IIT that showed a counter example that it does not form. So for that, we also found one condition that if AB equals to BA, then only it would form the group like that.
No, that's not right. So you're saying symmetric positive definite matrices, they don't form a group.
Yes, one example also they give that.
Give me the example.
1 minute, sir. A matrix is 2, 1, 1, 1.
No, but then 2, 1, 1, 1. And
Then B was 1, 1 by 2.
1, 1 by 2.
1 by 2, 1.
So the product of this
Is 2.5, means A into B is
2.5. So 5 by 2.
yes 2, 1 by 1.5, that is 3 by 2.
No, but this has to be symmetric, right?
Yes, that is not coming. We are telling that.
But the multiplication is not coming to be, the product is not coming, product under matrix multiplication is not coming to be symmetric.
Okay, but are you sure these are SPD matrices?
Yes, symmetric,
Yes,
and eigenvalues are also positive. That we can say that
Now, once again,
symmetric and eigenvalues are also greater than 0.
for both. Acha, let me check. Also 3 by 2. Okay, let me check this and then maybe I'll reply to you in an email. What is your ID number?
I typed in chat box.
Okay. So right. Sure. So let me think about this and I'll get back to you hopefully today.
Okay, sir. Thank you, sir.
Thank you. Right. Anybody else? Okay. So right. See you guys on post Diwali.
thank you, sir.